Hi everyone. Today we're going to study propositional function. There are statements that involve variables. Examples: x is greater than 3, x equals y plus 3, x plus y equals z. Computer X is under attack by an intruder. Computer X is functioning properly. These statements are neither true nor false when the values of the variables are not specified. We have here one example: x is greater than 3. In this example, we have two parts. The first part is the x, and we call that the subject. The phrase is greater than 3 is called predicate. Now for the notation, we write capital P of x, and we call this now the propositional function, where P denotes the predicate is greater than 3, and x is the variable, or we say the subject. The statement capital P of x is also said to be the value of the propositional function P at x. Once a value has been assigned to the variable x, the statement P of x becomes a proposition and has a truth value. Example 1. Let P of x denote the statement x is greater than 3. What are the truth values of P of 4 and P of 2? In this problem, we write the P of x, colon, x is greater than 3. Now let's begin with P of 4, meaning we will substitute this value 4 to the x on the right. So we have 4 is greater than 3. We know that 4 is greater than 3, and that is true. So the truth value for P of 4 is true. Now for the P of 2. We substitute the number 2 to the x. So we have 2 is greater than 3. And we know that this is false. So the truth value of P of 2 is false. So we have now the answers. P of 4 is true, P of 2 is false. Example 2. Let capital A of x denote the statement computer X is under attack by an intruder. Suppose that of the computers on campus, only CS2 and Math 1 are currently under attack by intruders. What are truth values of A CS1, A CS2, and A Math 1? Let us write the given. A of x, colon, computer X is under attack by an intruder. Let's begin with this A CS1. So we substitute this variable x by the computer. So we say that computer CS1 is under attack by an intruder. Because CS1 is not on the list of computers currently under attack, we conclude that A CS1 is false. Since CS2 and Math 1 are on the list of computers under attack, we know that A CS2 and A Math 1 are true. Example 3. Let Q of xy denote the statement x equals y plus 3. What are the truth values of the propositions Q12 and Q30? So we write the given qxy colon x equals y plus 3. Let's begin with q12. So the number 1 corresponds to x and the number 2 corresponds to y. We substitute respectively, so we have 1 equals 2 plus 3. Simplifying the equation, the right side becomes 5, and we say that 1 is not equal to 5. So the q12 has the truth value false. Next is the q30, and this is equal to the 3 equals 0 plus 3. When we simplify, 3 equals 3. So this is true. We know now the truth values of the propositions. q12 is false, q30 is true. I hope you learned something from this video. See you again next time. Hi everyone, today we're going to study an arypredicate. In general, a statement involving the n variables x sub 1, x sub 2, x sub 3 up to x sub n can be denoted by p of x sub 1, x sub 2, x sub 3 up to x sub n. A statement of the form p of x sub 1, x sub 2, x sub 3 up to x sub n is the value of the propositional function p at the n tuple x sub 1, x sub 2, x sub 3 up to x sub n. And p is also called an n-place predicate or a n-ary predicate. Example 1. Let R of x, y, and z denote the statement x plus y equals z. What are the truth values of the propositions R of 1, 2, 3 and R of 0, 0, 1? Let us write the given, the R of x, y, z, that is x plus y equals z. Now let's evaluate R of 1, 2, and 3. Remember, the number 1 corresponds to the x, the number 2 corresponds to the y, and the 3 corresponds to the z. Let us substitute the corresponding values on the equation. So we have this 1 plus 2 equals 3. Simplifying the equation, the left side becomes 3 and that is equal to 3. So the truth value of this R of 1, 2, and 3 is true. Let's go now to the R of 0, 0, 1. Substituting the corresponding values, we have now 0 plus 0 equals 1. Simplifying this equation, the left side becomes 0 equals 1. This is false. So the truth value for R of 0, 0, 1 is false. Example 2. Consider the statement, if x is greater than 0, then x colon equals x plus 1. When this statement is encountered in a program, the value of the variable x at that point in the execution of the program is not executed. So the value of x is not changed. I hope you learned something from this video. See you again next time. Hi everyone. Today we're going to study universal quantifier. There is another important way called quantification to create a proposition from a propositional function. Quantification expresses the extent to which a predicate is true over a range of elements. In English, the words all, some, many, none, and few are used in quantifications. The area of logic that deals with predicates and quantifiers is called the predicate calculus. Now let's study universal quantification. Many mathematical statements assert that a property is true for all values of a variable in a particular domain. Such a statement is expressed using universal quantification. Note that the domain specifies the possible values of the variable x. The meaning of the universal quantification of p of x changes when we change the domain. The domain must always be specified when a universal quantifier is used. Now we have universal quantifier. The universal quantification of p of x is the statement p of x for all values of x in the domain. The notation inverted A x p of x denotes the universal quantification of p of x. Here, this inverted A is called the universal quantifier. We read inverted A x p of x as for all x p of x, or for every x p of x. An element for which p of x is false is called a counterexample of for every x p of x. Note that if the domain is empty, then for every x p of x is true for any propositional function p of x, because there are no elements x in the domain for which p of x is false. Let's have example 1. Let p of x be the statement x plus 1 is greater than x. what is the truth value of the quantification for all x, p of x. The domain here is the real numbers. Because p of x is true for all real numbers x, the quantification for all x, p of x is true. Example 2. Let q of x be the statement x is less than 2. What is the truth value of the quantification for all x, q of x? The domain is the real numbers. Q of x is not true for every real number x. Let's find a counterexample. Let's say x is 3. So we have this q of 3. Substituting the number 3 to that statement, it becomes 3 is less than 2, which is false. That is, when we set x equal to 3, that is a counterexample for that statement for all x, q of x. Thus, for all x, q of x is false. Example 3. What is the truth value of the universal quantification of p of x, colon, x squared is greater than 0? The domain here, all integers. To show that the statement for all x, p of x is false, where the domain consists of all integers, we give a counter example. We see that x equals 0 is a counter example because x squared equals 0 when x equals 0, so that x squared is not greater than 0 when x equals 0. Therefore, for all x, p of x is false. Example 4. What is the truth value of the universal quantification of p of x, colon, x squared is less than 10? The domain here is positive integers not exceeding 4. The statement for all x, p of x is the same as the conjunction p of 1 and p of 2 and p of 3 and p of 4. Because the domain consists of the integers 1, 2, 3, and 4. Because p of 4, which is the statement 16 is less than 10, is false, it follows that for every x, p of x is false. In here, the number 4 is the counter example. I hope you learned something from this video. See you again next time. Hi everyone. Today we're going to study existential quantifier. Let's begin with existential quantification. Many mathematical statements assert that there is an element with a certain property. Such statements are expressed using existential quantification. With existential quantification, we form a proposition that is true if and only if p of x is true for at least one value of x in the domain. Let's have now the existential quantifier. The existential quantification of p of x is the proposition there exists an element x in the domain such that p of x. We use the notation reverse e of x p of x for the existential quantification of p of x. Here, the reversed e is called the existential quantifier. The existential quantification reversed e x p of x is read as there is an x such that p of x. Or it can be like this. There is at least one x such that p of x. Or it can be like this. For some x, p of x. A domain must always be specified when a statement for some x, p of x is used. Furthermore, the meaning of for some x, p of x changes when the domain changes. Without specifying the domain, the statement for some x, p of x has no meaning. Let's go now to the truth value of existential quantifier. The existential quantifier for some x, p of x is true if there is at least one x for which p of x is true. Or this is false if p of x is false for every x in the domain. Example 1. Let p of x denote the statement x is greater than 3. What is the truth value of the quantification for some x, p of x, where the domain consists of all real numbers? Since x is greater than 3 is sometimes true, for instance, when x equals 4. The inequality here becomes 4 is greater than 3. Then, the existential quantification of p of x, which is for some x, p of x, is true. Example 2. Let q of x denote the statement x equals x plus 1. What is the truth value of the quantification for some x, q of x? The domain here is the real numbers. Since q of x is false for every real number x, the existential quantification of q of x, which is for some x, q of x, is false. Example 3. What is the truth value of for some x, p of x, where p of x is the statement x squared is greater than 10. The domain here is the positive integers not exceeding 4. The domain is 1, 2, 3, and 4. And the proposition for some x, p of x is the same as the disjunction p of 1 or p of 2 or p of 3 or p of 4. Since p of 4, which becomes the statement 16 is greater than 10, that is the 4 square is greater than 10 is true. It follows that for some x, p of x is true. I hope you learned something from this video. See you again next time. Hi everyone. Today we're going to study the uniqueness quantifier. We have learned about universal and existential quantifiers. These are the most important quantifiers in mathematics and computer science. However, there is no limitation on the number of different quantifiers we can define, such as there are exactly 2, there are no more than 3, there are at least 100, and so on. Of these other quantifiers, the one that is most often seen is the uniqueness quantifier, denoted by reversed E with exclamation point or reversed E sub 1. The notation reversed E exclamation point x p of x, or this symbol, states there exists a unique x such that p of x is true. Other phrases for uniqueness quantification: there is exactly 1, there is 1 and only 1. Example, reverse E exclamation x. So we have this x minus 1 equals 0, where the domain is the set of real numbers. Our symbol here, or the problem, we will copy, where the domain is the set of real numbers, states that there is a unique real number x, such that x minus 1 equals 0. This is a true statement, as x equals 1 is the unique real number such that x minus 1 equals 0. I hope you learned something from this video. See you again next time. Hi everyone. Today we're going to study logical equivalences involving quantifiers. Statements involving predicates and quantifiers are logically equivalent if and only if they have the same truth value no matter which predicates are substituted into these statements and which domain of discourse is used for the variables in these propositional functions. We use the notation S logically equivalent to T. The symbol is like an equal sign. In here, we are using 3 horizontal line segment to indicate that two statements S and T involving predicates and quantifiers are logically equivalent. Example, show that for all x, the conjunction P of x and Q of x, and for all x, P of x, and for all x, Q of x are logically equivalent, where the same domain is used throughout. To show that these statements are logically equivalent, we must show that they always take the same truth value no matter what the predicates P and Q are, and no matter which domain of discourse is used. Suppose we have particular predicates P and Q with a common domain. We can show that for all x, the conjunction P of x and Q of x, and for all x, P of x, and for all x, Q of x are logically equivalent by doing two things. The first one is we show that if for all x, the conjunction P of x and Q of x is true, then the conjunction for all x, P of x, and for all x, Q of x is true. Second, we show that if for all x, P of x, and for all x, Q of x is true, then for all x, the conjunction P of x and Q of x is true. Let's begin with the first one. Let us show that if for all x, the conjunction P of x and Q of x is true, then the conjunction for all x, P of x, and for all x, Q of x is true. So suppose that for all x, the conjunction P of x and Q of x is true. This means that if A is in the domain, then P of A and Q of A is true. Hence, P of A is true and Q of A is true. Because P of A is true and Q of A is true for every element in the domain, we can conclude that for all x, P of x, and for all x, Q of x are both true. This means that the conjunction for all x, P of x, and for all x, Q of x is true. Second, let us show that if the conjunction for all x, P of x, and for all x, Q of x is true, then for all x, the conjunction P of x and Q of x is true. Suppose that the conjunction for all x, P of x, and for all x, Q of x is true. It follows that for all x, P of x is true, and for all x, Q of x is true. Hence, if A is in the domain, then P of A is true, and Q of A is true. Because P of x and Q of x are both true for all elements in the domain, there is no conflict using the same value of A here. It follows that for all A, the conjunction P of A and Q of A is true. Consequently, for all x, the conjunction P of x and Q of x is true. We can now conclude that for all x, the conjunction P of x and Q of x is logically equivalent to the conjunction for all x P of x and for all x Q of x. Take note that this logical equivalence shows that we can distribute a universal quantifier over a conjunction. Furthermore, we can also distribute an existential quantifier over a disjunction. However, we cannot distribute a universal quantifier over a disjunction, nor can we distribute an existential quantifier over a conjunction. I hope you learned something from this video. See you again next time. Hi everyone. Today we're going to study negation of quantified expressions.